Hello, class. We are ready to move on to the next section. This one deals with the Pythagorean theorem. If you'll recall, a couple of lessons back, I mentioned it, and here we are now officially dealing with it. So the Pythagorean theorem is a very useful um, theorem that we use a lot in everyday life, particularly if you're doing construction or something like that. It's extremely useful. So I think you will find this one practical and hopefully enjoyable. Sorry I didn't get a lesson up yesterday. I had a serious situation that arose that demanded a lot of my time, and I spent a good many hours in meetings yesterday. So I feel badly about that, but probably you don't feel so badly, I'm guessing. Hey. In any event, we're pressing on. We have a couple more sections in chapter 10. This one on Pythagorean theorem, and then we'll go to trigonometric ratios, sine, cosine, and tangent for solutions to triangles. And following that, we will move on to chapter 11. So here's what you can expect as we move forward. We have a test over chapter 10, and then we'll move into chapter 11, and we'll have a test over that, and that will mark the end of your Algebra 1 course. So I would encourage you to begin reviewing chapter 10. When you have a free day, kind of like you did this last time here yesterday, I would encourage you, watch the videos again, take notes. This is really important. Take notes. Take a little notebook, and as you watch the video, write down the examples, any rules that are given or operations, methods of dealing with various equations, write them down so that you can go back and you can review quickly, and hopefully it will not take much of your time. So yeah, just taking notes is a good practice to get into, and I believe it will also help it to stick in your mind a little more firmly. So with all of that said, let us jump over now to study the Pythagorean theorem and do some examples. I believe you'll find this a little easier. I hope so. Now, the Pythagorean theorem applies to right triangles. Right triangles. Now, in a right triangle, this right here, this little symbol, the square in the corner like that, is the symbol we use to represent a right triangle. This angle right here, by right, we mean a 90-degree one. This is 90 degrees. Okay? So there's your 90-degree angle. Now, when we have right triangles, we talk about the legs and we talk about the hypotenuse. The legs and the hypotenuse. The hypotenuse I've labeled. The hypotenuse is always opposite the 90-degree angle. So notice the hypotenuse is there. It's opposite the 90. Okay, always opposite the 90. And the other two sides are called legs. This is a leg. This is a leg. So you have two legs, and then you have the hypotenuse. The hypotenuse is always the longest side. Notice this. This is the longest. So you have two legs, and then you have the longest side. The Pythagorean theorem is a very simple relationship. It says that the sum of the squares of the two legs is equal to the square of the hypotenuse. A squared plus b squared equals c squared, right here. A squared plus b squared equals c squared. This is the Pythagorean theorem. So the hypotenuse squared is equal to the sum of the squares of the two legs. So a squared plus b squared equals c squared. Now, a and b can be flipped around. You could have A being where B is and B being where A is. You could reverse the two, it doesn't matter. All you're doing is squaring them, each one individually, and adding them together. So A squared plus B squared equals C squared. Let's take a little example and see how this works. So I'm going to give you a triangle, and you are going to find the hypotenuse. So here we go, example number 1. We have a little right triangle. Let's draw it right over here. Here it is. Sorry for a very sloppy triangle. It's a little better. So let's say that this is 4 and this is 5. Okay, does that look reasonable? 4, 5. 5 does appear to be slightly bigger than the 4, but be careful. Sometimes things are not drawn to scale. Use the numbers that are given. So C over here, the hypotenuse, is going to be as follows. C squared is equal to 5 squared plus 4 squared. And what's 5 squared? 25. 4 squared is 16. And what is 25 plus 16? Well, it's 35, is it 41, is it? Yeah, 16, 11, 41. Okay, so C squared is equal to 41. So what is C? C will be equal to taking the square root of the left and the right. C will be equal to the square root of 41. 41 is a prime number, so there's nothing we can do with this one. We just leave it the way it is. Square root of 41, that's C. All right, simple enough. Let's do another example. Moving right ahead. Example number 2. Okay, in example number 2, we're going to have a right triangle that looks like the following. There's our 90-degree angle there. And let us put some lengths on here. Oh man, what did I just do? That's a little better. So let's put some lengths on this and see if we can find the unknown side. Let's say that this one is 13, and this is 5, and this is 12. Well, I just blew it. This is, let's say this is A. So 5, 13, and A. So what is A? Well, we know that A squared plus B squared, and 5 is the B here, is equal to C squared, which is 13 squared. So the sum of the squares of the two legs, here are my two legs, okay, this one and this one. You square these guys and then add them together, okay? And that's equal to the square of 13. So A squared plus B squared equals C squared. So can we find A squared? Yes, we can. A squared is going to be equal to 13 squared minus 5 squared. And what is 13 squared? 13 times 13 is 169 minus 25. Okay. 169 minus 25, which comes up to be what? 169 minus 25 should be, yeah, 144. So a squared is equal to 144. So if it's 144, then what's a? Well, the square root, let me do this again just to make sure we're all together, of a squared is equal to the square root of 144. Square root of a squared is just a is equal to square root of 144 is 12. Remember, we're dealing with principal square roots because when we're talking about the lengths of sides of a triangle, they must be positive. You don't have negative length. So a equals 12. Notice the relationship here. 5, 12, 13. The three are all nice, what we would call counting numbers. They're whole numbers. They're not like fractional or decimal or something of that nature. These are whole numbers, and there are three whole numbers representing the sides. We call this thing here Pythagorean triple. Pythagorean triple. 5, 12, 13. Let's take a look at another Pythagorean triple. Another Pythagorean triple. Example number 3. Okay. Let's draw another right triangle here. How should we do this one here? Let's draw it like this. Let's say that this is 5, this is 3, and this is a. Find a. Okay. Which side is the hypotenuse? It's the longest side. And the longest side is always opposite the 90-degree angle. Stand at the 90-degree angle, look across the triangle. The side opposite you is the hypotenuse, okay? So we know then that a squared plus 3 squared is equal to 5 squared. A squared plus b squared, this one squared plus this one squared equals the 5 squared. So a squared is just a squared. 3 squared is 9. 5 squared is 25. So a squared is equal to 25 subtract 9. 25 subtract 9. So a squared is equal to 16. So a is equal to the square root of 16, or 4. A equals 4. So here's your answer. A equals 4. So if I scroll back up here and label this, it's equal to 4. Notice this Pythagorean triple, 3, 4, 5. This is a 3, 4, 5 right triangle. It's a convenient one because all three of the sides are integers. It works perfectly. 3 squared plus 4 squared is equal to 5 squared. Okay, let's move on to another example. Example number 4 coming up. Example number 4. So in this example, we're concerned to know if these sides are the sides of a right triangle. Is this a right triangle? That's the question. 28, 45, and 53. So as you look at that, 28, 45, and 53, ask yourself, which are the legs and which is the hypotenuse? Remember, hypotenuse is always opposite the 90-degree angle, and it will be the longest side of the triangle. So you see 28, 45, and 53. If this in fact is a right triangle, then 53 must be the hypotenuse. So to check to see if this is a right triangle, all you have to do is work out the Pythagorean theorem. Is 53 squared, is this, question mark, is this equal to 28 squared plus 45 squared? Remember, sum of the squares of the two legs equals the square of the hypotenuse. So here's your question. Are these in fact equal? So again, 53 squared would have to be equal to 28 squared plus 45 squared if this was a right triangle. So are they equal? Well, 28 squared is 784. And 45 squared works out to be 2025. What is 53 squared? That is 2,809. Is the left equal to the right? That's the question. So is 2809 equal to 2025 plus 784? 2809. So what do you think? Is a squared plus b squared equal to c squared? Well, according to what we've just seen here, yes. 2809 equals 2809. And the way we show that we've done it, we have our thing proved. We say check. Yes, this is a right triangle. Okay. It is a right triangle. Okay, moving on now, we will do another example, example number 5. Example 5. In example 5, we have a square. And let me see what I can draw here. A square, hopefully I don't get it messed up. So here's our square. It doesn't look so great, does it? Yeah, that looks a little better. So this is a square. And as a square, we know that squares have right angles. They're a special type of a quadrilateral. Square is a special type of rectangle where sides are equal. Let's say that the sides of this particular square are all equal to 90 . Let's say it's equal to 19 meters. The question is, what is the diagonal? What is the length from here to here? What is that length in red? I'm going to label it as a D there, D for diagonal. what is the length of the diagonal? So if this is 90 and this is 90, so is this over here too? This is also 90. So 90 squared plus 90 squared must be equal to b squared. So how does this look right here? So d squared is going to be equal to 8100 plus 8100, which is equal to 16,200. So d will have to be equal to the square root of 16,200. So let's go ahead and work that out. So adding these two together then, we get 16,200. We take the square root of the left and the right, and d then comes up to be approximately equal to the square root of 16,200, which is 127.28 to the nearest hundredth. One 27.28 feet. One 27.28. Okay. Now I want you to look at this problem a little bit and notice something. When you have a square, the sides are the same. So 90, 90, and then d being the diagonal or the hypotenuse of the triangle there, 90, 90 are the two legs and d is the hypotenuse. There's a special relationship that exists in this particular thing. I want you to look at the square root of 16,200 and see if it cannot be simplified down a little bit. See if we can't simplify this down a little bit. D squared, or sorry, D, not B squared, D is equal to the square root of 16,200, right up here, this number. How could we write that? Let's see if we can write it differently. It's going to be equal to 2 times what number? 8,100 from up above. Do either one of those numbers have a nice square root? Well, we can write this as the square root of 8,100 times the square root of 2. Square root of 8,100 is just 90. Square roots of 2 feet. Look at this now. D is equal to 90 times the square root of 2. Interesting relationship. Let's take a generic triangle now as another example, a generic one. And let's see what we can come up with for example number 6. Example number 6. In example number 6, we're going to label this length here L, this length here L, and the question is, what is C? Okay, L, L, and C. Now, if you notice, the L's are the legs. C is the hypotenuse. If the legs are equal, as they are in this case, L and L, or 90 and 90, what can you say about this triangle's angles? Well, you know the sum of the angles in a right triangle or in any triangle rather, is equal to 180. If this is 90 right here, these other two must be what measure? Can you tell me what the measure of these two angles is? They're 45, aren't they? 45 and 45. So this thing then should be c squared is equal to L squared plus L squared, or 2L squared, that's c squared. So c must be equal to the square root of 2L squared, okay, which you can rewrite as the square root of L squared times the square root of 2. That's equal to c squared, or c rather, sorry, not c squared. It's just equal to c. c is equal to the square root of L squared times the square root of 2. The square root of L squared is simply L, and you get L times the square root of 2. Notice that in example 5, we've got 90 times the square root of 2. In example 6, we've got L times the square root of 2. It turns out that when you have a 45, 45, 90 right triangle, the sides will always be L, L, L square roots of 2. Okay? So once again, L, L, L square roots of 2. So memorize this pattern. A 45, 45, 90 is an isosceles triangle where you have two angles being the same. Okay? And it's always in this relationship L, L, L squared to 2. Okay? Memorize that little rule. This is a special right triangle. L, L, L squared to 2. Let's look at number 7. In example number 7 is also a special type of right triangle. So here we have another special right triangle, a 30, 60, 90. 30, 60, 90 is a very common type of triangle. The sides, again, have a special pattern. If the short leg is L, if the longest side is 2L, then the question is, what is the third side? So the third side is what we're looking for. What will be the application here of the Pythagorean theorem? So the sum of the squares of the two legs must be equal to the square of the hypotenuse. So then I'm going to call this other leg here, and instead of a question mark, let's label it as B. Doesn't really matter. Let's just call it B. So B squared must, sorry, wrote that incorrectly. Let's get a little more room. Let's do it down here. B squared plus L squared must be equal to 2L quantity squared. Okay? In other words, A squared plus B squared must be equal to C squared. C is 2L, so 2L squared, okay, must be equal to B squared plus L squared, the sum of the squares of the other two legs. Okay, so B squared itself must be equal to 2L quantity squared minus L squared. And 2L quantity squared is 4L squared. So B squared must be equal to 4L squared minus L squared, which is 3L squared. So B itself must be equal to the square root of this particular number, which we can simplify down nicely. So B will be equal to the square root of L squared times the square root of 3. The square root of L squared is just L. And it turns out that B is equal to L times the square root of 3. This is an important relationship right here. So when you look at our special right triangle, the 30, 60, 90, notice how the sides work out. The sides will be L, 2L, and then this side over here becomes L times the square root of 3. So L, 2L, L squared, it's a 3. Here's the relationship. L, 2L, L squared, it's a 3. And 2L is the longest, and it is the hypotenuse. Remember, the hypotenuse is where? It's the longest side, and it is opposite the 90-degree angle. So again, L, 2L, L squared, it's a 3. So if I were to tell you, example number 8 down here, if I were to give you a 30, 60, 90, and I were to tell you that this side was equal to 5, what are the other two sides? Well, if this is L, okay, then this side over here is 2L, which is equal to 2 times 5, or just 10. And this side over here must be equal to 5 times the square root of, that's a great looking square root, 5 times the square root of 3. 5 square roots of 3. So notice 5, 10, 5 squared is 3. Simple enough. Once you know the rule for the special right triangle, it becomes very easy to solve that. Now, do you have to have this knowledge in order to solve this triangle? No, you don't. If you were given two sides, you can always find the third. But in this case, if you are not given two sides, you're only given one side like this, 5. You know it's a 30, 60, 90. You can immediately write down the other two sides with no algebra at all. You can just write it down if you have it memorized, this pattern. So this is another special right triangle. L, 2L, L squared is a 3. Okay, very good. Okay, let's try another problem. How about example number 10. We'll try to liven this up just a little bit and give you a tougher problem. So here, let's make a cube. Let me see if I can draw a cube. I hope I can make a nice one. You know what a cube is, right? It's a rectangular solid where all sides are the same length. So in this problem, we are looking for the diagonal of a cube. Diagonal of a cube. And if the side of the cube is equal to 5, then what is the length of that blue line, the diagonal? I've tried to draw 3D. It's a little tough, but I hope you can visualize what's going on. Since it's a cube, that means all the angles are right angles in the corners. So if finding the blue line becomes a matter of solving a right triangle using the Pythagorean theorem. So this is also 5 going up here, the vertical height. How do we find the blue line? Well, we need the diagonal of the base. The diagonal of the base. Let's see if we can draw in the diagonal of the base. So here we go, diagonal of the base. Like this. Okay. And of course, this remaining side is right here. This is my remaining side. So I want to solve this particular right triangle right here. The angle in the corner, as I've already mentioned, is a right angle. That's a right angle. So 5 is our height, and we need the diagonal across the base, which is going to be equal to 5 times the square root of 2. Why do I know that? Because look at the relationship here, 5 and 5. These guys right here form the sides of a right triangle, where this is a right angle down here on the bottom, and the 5 and 5 are the sides, and because it is a cube and all the geometry measures up, you know that this angle right here you know that this angle right in here is 45 degrees. That means that one up there is also 45. So it's 45, 45, 90. That means the distance across the base here is going to be equal to 5 times the square root of 2. Remember, it's L square roots of 2. And it's 5, 5, 5 square roots of 2. Okay, so now we have a right triangle where the one leg is 5 square roots of 2. The height is 5. So we have this one, 5 square roots of 2, and then we're looking for the blue diagonal, which I'm just going to label as D. So we're looking for D. So how do we find it? Well, we go back to this, D squared is equal to 5 squared plus 5 squared, so 2 squared. That's our Pythagorean theorem. A squared plus b squared equals c squared. D is our diagonal. Where did it go to? I thought I labeled it in here. D is our diagonal, so D squared is going to be equal to 5 squared plus 5 squared to 2 squared. So we go ahead and work this out. 25 plus this squared is 25 times 2, or 50. So d squared then comes up to be equal to 75. And so d, coming right on over here, is going to be equal to the square root of 75. It turns out that that is a nice number to work with because it's the square root of 25 times what? Times 3. 25 times 3, which is square root of 25 times the square root of 3, or 5 square roots of 3. D is equal to 5 square roots of 3. There you have it. It's an interesting problem. Hope it makes sense to you. Yeah, it's a nice one. Good problem. Okay, well, I think that sums it up for today. Go ahead and study hard. I suggest you run through all of these examples again. Study this video, write down the examples, work them out for yourself until they make sense to you. Okay? If you can't reproduce these, then you know you are not quite where you should be. So work with this until you can reproduce these. We're moving a little slow, so you really have no excuse for not learning this stuff. Take the time every day. You need to be spending at least an hour a day, hour to an hour and a half. On a hard day when there's, a big assignment, or maybe you have a test the next day, you would spend more than the usual. You might spend 2 to 3 hours studying. But generally speaking, an hour a day or thereabouts should, for the most part, take care of your video viewing and some review. So with that said, I want you guys to concentrate on preparing for a test, because there will be a test. That's right, there is a test coming. At the end of this chapter, we're going to have an exam over chapter 10. Chapter 10, radical equations, radical expressions. And at the end here, of course, the Pythagorean theorem, and then trigonometric ratios, sine, cosine, and tangent, which we'll be covering next time. So I'll get you an assignment up sometime this morning, and it'll be due as usual by 11:59 Tuesday evening. So best wishes to you. If you need to ask any question, you can always text me on WhatsApp. All right? You guys have a good day.